Hello students, today in this video we are going to study about the magnetic field on the axis of a circular current loop. So previously we have already studied that if we have a current loop then what will be the magnetic field because of that loop at its center. Now we are going to find the magnetic field because of that loop on the axis of it. That means we are having a circular loop of a wire. Let the radius of that loop be small a, and it carry a current of capital I, and we are assuming that the plane of the loop is perpendicular to the plane of paper, right? So जब हमने center पे magnetic field निकाला था, at that time we were considering the loop in the plane of the paper. But while doing this, while we want to find the magnetic field on the axis of a circular current loop, then in this case we are going to consider the loop such that the plane of loop is perpendicular to the plane of paper. I am going to show you that in the diagram. So here in the diagram I have considered a loop of radius small a. So this radius of the loop is small a. This is the center of the loop. Let it is denoted by C. C is the center of the loop and this is the radius small a, and current capital I is flowing in the along the loop, along the wire, and the point we have considered on which we are going to take our observations, that is a point on axis. Let this point be capital P. So P is a point on the axis of the loop where we want to find the magnetic field because of this whole loop. So our task is to find the magnetic field at point P which exists on the axis of the loop, right? And because of the magnetic field that we are going to find, that is because of this loop only. So according to Biot-Savart law, what is the procedure? That you have to divide this loop into different segments and consider one of the segment that we called current element and find the magnetic field strength at point P because of that single current element, and after that we will integrate that magnetic field for the whole loop. So we have to consider a single segment, or I can say a current element. Let that current element I am considering here. So this is a current element of length dl vector that I am considering for our calculation, and the direction will be like this because current is flowing in this direction. Now one more thing is here, the loop that we considered is perpendicular to the plane of paper. So here I am showing you half of the loop with a bold line while half is from dotted line. This shows that the loop is like this, the plane of loop is like this, and this half is across the paper, means वो पेपर के दूसरे साइड में है, while this half is above the paper. So this half is below the paper and this half is above the paper. It's like this. This is the plane of the loop and we want to find the magnetic field because of this loop at point P, which is at the axis of the loop. For that we consider a single element. So for this current element we are going to find the magnetic field strength first, and after that we will integrate that magnetic field strength over the whole loop. So let the distance of this current element from the point or from the observation point be S vector. This is the position vector of point P or the observation point from current element, right? And the angle that is formed here, let that angle be phi. Similarly, we can also consider an element here, right? This symmetrically. So this is also of the length dl vector. We considered it here just opposite to this one, and the distance again, if we see, will be S vector only, and the angle will also be same, that is phi. Alright, okay. So we have considered a current element at the top and the other one at the bottom. First we are talking about the current element that is at the top of the loop, as it has an outwards current coming, like outward coming current, like जो loop है वो बाहर है पेपर के and the current is coming outwards along the loop. So what is the magnetic field at point P because of this current element? First we are going to see that. So according to Biot-Savart law, the magnetic field dB is equal to, I am writing the magnitude only, dB is equal to mu naught upon 4 pi I dl, okay, sine theta upon r square, but the distance is s here, so it will be s square. So mu naught upon 4 pi I dl sine theta and upon में s square. Now dl vector and s vector are perpendicular to each other. The angle theta is the angle between current element and the position vector, means dl vector and s. So dl vector is perpendicular to the plane of paper and s vector is in the plane of paper. That's why this is the system. So जो dl vector है वो इस तरीके से है, plane के perpendicular, paper के plane के perpendicular, and s vector is in the plane of paper. So the angle between dl vector and s vector will be 90 degree. So this implies that theta is equal to 90 degree because dl vector is perpendicular to s vector. In that case, the magnetic field dB is equal to mu naught upon 4 pi I dl, and sin 90 is 1, so I dl upon s square. This is the magnetic field because of this current element at the top. Okay, this is the magnetic field because of this current element at the top. So this was the magnitude of the magnetic field. Now we are going to talk about the direction of the magnetic field. So the field dB vector actually lie in the plane of the paper, right? जब हम loop को पेपर के प्लेन में कंसीडर करते हैं, देन जो dB का डायरेक्शन हमको मिलता है वो परपेंडिकुलर टू द प्लेन मिलता है. बट राइट नाउ वी आर हैविंग द लूप परपेंडिकुलर टू द प्लेन ऑलरेडी, मीन्स पेपर के प्लेन के परपेंडिकुलर है लूप. तो इसकी वजह से जो मैग्नेटिक फील्ड हमें पॉइंट पी पे मिलने वाला है, इट विल बी इन द प्लेन ऑफ पेपर एंड इज परपेंडिकुलर टू एस वेक्टर. So we can show it somewhere like this. This will be the direction of magnetic field at point P because of the current element dl vector. I am going to denote it by PQ. Okay, so the point is कि जो field dB vector है, it will lie in the plane of paper and is perpendicular to s vector and shown by PQ vector. Okay, right. So phi is the angle. Now we know that the phi is the angle we have considered. Phi is the angle between CP and I am considering it as O. Then CP and OP के बीच का जो angle है, that is phi. So dB को हम दो components में resolve कर सकते हैं. So this dB can be divided into or resolved into two components. This is the direction of dB vector acting here, and it can be resolved into two components like this. Okay, कैसे होगा ये component में division? Now this is angle phi and this is angle 90, right? This is phi, this is 90. So this angle, this remaining angle is 90 minus phi. Again, what we know that the direction PQ is perpendicular to s vector, so this whole is 90, but this was 90 minus phi, so again this angle will be phi. Let us write it as, from this component, if we see the angle, this angle CPO is phi, angle made by the component this whole angle is 90 degree, so the remaining angle is 90 minus phi. Okay, but we know that the dB vector is perpendicular to S vector, so this whole is 90, so the remaining angle, this is also phi. Now this remaining angle is phi, so the components can be written as dB cos phi, angle के साथ वाला जो component है, it will be the cosine component, and dB sin phi. Okay, dB cos phi and dB sin phi, these are the components. dB sin phi is along the axis, while dB cos phi is perpendicular to the axis of the loop. Now we consider another current element that is diametrically opposite to the first one. So we have considered first current element at point O. Now we are considering the other current element which is diametrically opposite to this one. This diametrically opposite means जितना ये इधर था उतना ही ये वाला element इधर है. Then from this element, because of this element, the magnitude of magnetic field will remain same, and again the components, the direction, first of all the direction, if we see the direction, then we get direction perpendicular to S vector like this. So let us denote it by PQ dash, and again this magnetic field, let it be dB vector because the magnitude is same. So this magnetic field again resolved into two components. Similar process, this angle will be phi, and it will be divided into two components, dB cos phi and again dB sin phi. Okay, so dB cos phi perpendicular to the axis, while dB sin phi along the axis of the loop. So what we are concluding here is that in such a system, for any two diametrically opposite elements of the loop like this, the components perpendicular to the axis of the loop will be equal and opposite and will cancel out. Here we can see that the dB cos phi here and here are same in magnitude but opposite in direction, so these will cancel out, and the net effect that we get, it will be because of these sine components along the axis only. So for two diametrically opposite elements of the loop, the components perpendicular to the axis of the loop will be equal and opposite and will cancel out, while their axial components, जो components axis के along होंगे, will be in the same direction, that is along the direction CP, C to P, along this direction C to P, and get added up. So the total magnetic field at point P जो हमें मिलने वाला है, it is because of the addition of these components only, right? And it will be in the direction CP. So let's find the total magnetic field. Total magnetic field at point P in direction CP. B is equal to, तो अभी हमें dB sin phi के जितने components हैं उनको add up करना है, तो let us integrate dB sin phi for all the components, like for all the current elements. जितने भी हम current elements consider करेंगे, सबके लिए जितना dB sin phi आएगा सबको हमें add up करना है, and it will give the magnetic field, total magnetic field because of the loop. So how we will do this? We know that from the diagram sin phi is equal to, now sine is perpendicular upon hypotenuse, so sin phi is equal to A upon S, and dB is equal to mu naught upon 4 pi I dl upon S square, that we have calculated here. So we will substitute these values in this formula, right? Then we get B is equal to integral mu naught upon 4 pi I dl upon S square into A upon S. On solving this, we get B is equal to mu naught I A upon 4 pi S cube and integral of dl. So we are going to integrate dl for the whole length of the loop, and the whole length of the loop means the circumference of the loop. This is the circumference of the loop, and the radius of loop is a, so its circumference will be 2 pi a, right? So integral of dl actually means circumference in case of loop. So b is equal to हो गया म्यू नॉट आई ए अपॉन 4 पाई एस क्यूब इंटू 2 पाई a. On solving we get b is equal to mu naught I a square, mu naught I a square, and upon 2 s cube, right? But we can write s as under root r square plus a square by applying Pythagoras theorem. So b can be written as b is equal to mu naught I a square upon 2 r square plus a square power 3 by 2. This is the value of magnetic field at point P, but this is the actually magnitude, and its direction will be along CP. So the direction of field is along positive x-axis. If we see from here, so this is the direction of positive x-axis, and we can write it as by using I cap with the magnitude. Hence, to denote the positive x-axis direction, we can write it as b vector is equal to mu naught I a square upon 2 r square plus a square power 3 by 2 I cap, means along positive x-axis. All right. So this was the case when we have a single loop, means this is the magnetic field because of a single current loop at its axis. If we have a coil that consists of n turns, then this value becomes n times of the value that we get from single loop. So for a coil having n turns, we get b vector is equal to mu naught n I a square upon 2 r square plus a square raised to 3 by 2 I cap. So this is the value for a coil having n turns, and it will also along positive x-axis. Now there are some special cases also, so let's talk about these special cases. So let's move to the case 1. We know that the magnetic field B is equal to mu naught n I a square upon 2 r square plus a square power 3 by 2 for a point at the axis of a circular loop or a coil having n turns. Now the special case is we want to find the magnetic field at the center of the loop. अगर आप loop के center पे निकालना चाह रहे हो, so when you talk about the center, the distance r, that is the distance from C to P. So r is the distance actually C to P. We have the diagram like this, na? Here was the radius A, this was point P, this was point C, and current element dl. This was the radius, and the distance of point P from this current element is S, and this CP is R. That's why we put here by using Pythagoras theorem, s cube को हमने under root r square plus a square का cube substitute किया था. So when we talk about the center, that means this point P is at C only, and the value of r is 0. So for the center r is equal to 0. In that case b is equal to हो जाएगा mu naught n I a square upon 2 a square का 3 by 2, that means mu naught n I a square upon 2a cube. When we solve it, we get b is equal to mu naught n I upon 2a. So this is the value for the magnetic field at the center of a current loop. The second case is at the axial point lying far away from the coil. Means we are going to find the magnetic field at point P, but this point P is lying very far from the coil. So the case 2 is at axial point lying far away from the coil. So actually this means the distance r is very large, or we can apply the condition that r is greater than a. Means in this formula we are going to apply the condition that r is greater than a. So when we apply this condition कि r a से बहुत बड़ा है, that means we can neglect a in comparison to r. So here in this bracket we are going to neglect a in comparison to r. So we will get b is equal to mu naught n I a square upon 2, and we are going to neglect a square, then it will be 2r square power 3 by 2, and this will give us b is equal to mu naught n I a square upon 2r cube, right? B is equal to mu naught n I a square upon 2r cube. This field is directed along the axis of the loop only, and point P is lying far away. That's why we take r is greater than a and neglect a in this formula, but the direction of the field will remain same, that is along the axis of the loop only, right? Case third, coming to the case third. Now the case third is at an actual point at a distance equal to the radius. Means point P is lying at the circumference of the loop or at the surface of the loop. Means third case is at an axial point at a distance equal to the radius of the coil. That means distance r is equal to distance a. So if we have the formula b is equal to mu naught I a square upon 2r square plus a square raised to 3 by 2, and we are considering the case where r is equal to a, so we will substitute this to this formula and get b is equal to mu naught n I a square upon 2 a square plus a square raised to 3 by 2. On solving this we get mu naught n I a square upon 2 twice of a square raised to 3 by 2, right? And on solving this what we get, mu naught n I upon 2 raised to 5 by 2. So numerator is a square, denominator is a cube. So finally we will get on solving b is equal to mu naught n I 2 raised to 5 by 2 into a, right? This is the value of magnetic field at a point on the axis but at a distance equal to the radius of the coil. Okay, so let's talk about the variation of magnetic field along the axis of a circular current loop graphically. If I want to show the graphical representation of variation of magnetic field along the axis of a circular current loop, then I will get the graph like this. Okay, so this is the distance on x-axis, that is independent, and this is magnetic field on y-axis, which is a dependent factor. And if we plot a graph, then we get a curve like this. Okay, now let us explain this, how we are getting this. Suppose this is the center of the loop and loop is placed here, and this is the center. So at the center of the loop we will be getting the maximum value of magnetic field. If if we are seeing the value of b, then the value of b is maximum at the center, and as we move away from the center in either direction, so in both the directions, as we go away from the center of the loop, it decreases, the magnetic field decreases on both the side of the loop. So this is the variation of the magnetic field along the axis of a circular current loop. So this was all about the magnetic field on the axis of a circular loop, right? We will be studying about solenoid in the next video. So till then, keep studying and stay tuned. Thank you.